All right. Continuing on here with our discussion of some of the structures we can draw here for the molecular formulas we're looking at. We finished off methane back here, right? 4 bonds to the carbon, 1 for each hydrogen, like we'd expect from the formal charges we've been developing. Right, now what if there's more than 1 carbon? So we need to think a little bit about how this would affect the skeleton. So looking at the formula here, 2 carbons, 6 hydrogens, I know that I can't make more than 1 bond to a hydrogen in my structure. So that should lead me to recognize that if I have 2 carbons here in the structure, they need to be connected to each other. Because if they aren't connected to each other, how could they both be in the same molecule if we don't have any other atom that could bridge between them? So you'd start drawing here by putting the 2 carbons together. And then we could think about filling in 6 hydrogens. You can put 3 hydrogens on each carbon, right? You don't go past 4 bonds with a carbon because that would take us past 8 or past the octet rule, and we don't want to do that. But since we have 6 hydrogens, we can put 3 on each of the carbons. Now, that gets us to a point where each carbon has 4 bonds, right? So that would satisfy the octet rule. It would also give it a 0 formal charge. Each hydrogen has 1 bond. That satisfies the duet rule for hydrogen and gives it a 0 formal charge. So there's our structure. The 2 carbons are connected, right? But then they each have 3 hydrogens around them. Now, one of the things that is particularly compelling about carbon compounds is there's a lot of variability. We can start to think about what if there's fewer hydrogens involved. Now, the same is true for the analysis of the skeleton, as we can start with recognizing that the carbons would have to be connected to each other, right? Otherwise, in this case, they can't be in the same molecule because we can't bridge a hydrogen between them. That would require making 2 bonds to the carbon, to the hydrogen. But with only 4 hydrogens, there's actually 2 different ways we can think about drawing in the hydrogens, and we might need to figure out which one of those kind of fits the rules we've been describing. So 2 places to put hydrogens. One option would be 3 on 1 carbon, 1 on the other. And the other option would be 2 on each, like so. Right? Now, either of those skeletons, right, we can work through the rest of the steps and figure out if that gives us a good structure. Does it satisfy the rules we've been thinking about? So if I look at this structure, so total electrons here would be a good thing to think about as well. 4 for each carbon would be 8, plus another 4 for hydrogen would be 12 total. Now I made 1, 2, 3, 4, 5 bonds here, and that means I used 10 electrons already. I've only got 2 left. Now the only atom here that hasn't satisfied how many electrons it needs is this carbon. So I could put those last 2 electrons on that carbon. But now I couldn't make another bond. I can't share them here because this carbon already has 8. I can't take any more. You can't share them and make another bond with the hydrogen. There are no movable electrons to kind of bring in and bring up the electron count on this carbon. So what we have here is a 6 electron count carbon, right? We're trying to avoid that. So that's a pretty good indication that maybe that wasn't a good skeleton. We just weren't able to get to a good structure. Now over here though, this is also 1, 2, 3, 4, 5 bonds made, 10 electrons, so just 2 more left, right? But if I draw them in on one of the carbons, and then I count my electrons, 8 here, 6 here, in this case, I actually can share and use that pair of electrons to make a double bond. 4 shared electrons between the 2 carbons. And if I do that, I get a good structure. I have 4 bonds on each carbon, which gets it to the octet rule and to a 0 formal charge. I have 1 bond for each hydrogen, which gets them to their duet and a 0 formal charge. So in this case, I need a double bond, right, based on the formula there. So that is the appropriate structure. This is something you may have to do by trial and error, right? Try some different skeletons, see what you can get to work in terms of the structure, right? And you may be able to eliminate some as you just can't draw an appropriate structure with that particular set of atoms in that arrangement. Okay, so moving on to the next page, if we drop the hydrogen down even further, right, we have additional options. So C2H2, right, again, we know, or we should be able to figure out, I better connect the carbons. But there are two different ways we can think about here as well. One would be, let's just put one hydrogen on each of the carbons. And the other one would be, let's put both hydrogens on one of the carbons. Okay. Now, 2 carbons would be 8 electrons, 2 hydrogens would be 2 more, that's 10. Right? And we used 2, 4, 6 already, so we have 4 left. So maybe you could do something like this, put 2 on each carbon, right? But certainly you would recognize after putting in the electrons, this carbon doesn't have enough, this carbon doesn't have enough, I really need to share. So all of these electrons would end up having to be shared between the carbons to make a triple bond, right? But that would get us to 4 bonds for each carbon, a 0 formal charge for each carbon, right? And 1 bond for each hydrogen, which would also be good. So we can get a good structure that way. What about this one? This carbon already has 3 bonds. We could add 2 there. So 2, 4, 6, we used 6 electrons. We have 4 left, right? We would usually want to put them on the periphery, though, instead of the central atom. So let's start them over there and see what we can do. This carbon is shy of electrons. So is this one. So maybe we make things a little better if we start to share. Right? But that's all we can do. We can't share this pair anymore. We again end up with a 6 electron carbon, which is not good. So this skeleton that we started with just doesn't lead to a good structure. We'd have to use this other possible way to attach the carbons and the hydrogens. Okay. Now, the next one I have on my list is SCN. I'm actually going to jump ahead to carbonate here, carbonate ion, because it'll be a little easier to talk about the remaining issue that we need to talk about. And then we'll come back to SCN and see why that's maybe a slightly more complicated case. So for carbonate, though, so let's count the electrons first to account for that charge. Carbon has 4. We have 3 oxygens, each brings 8, so that would be 16. 3 oxygens. Okay, talk and write at the same time, not good. Carbon has 4, 3 oxygens, each oxygen has 6, so 6 times 3 is 18 total from the 3 oxygens. The charge here is -2, that means there are an additional 2 electrons here. So there are a total of 24 electrons we want to draw here for carbonate. Now, carbon is less electronegative than oxygen, so we should probably recognize carbon should go in the middle of our structure, and we want to attach the oxygens to it, like so. Okay, that used up 6 electrons to make those 3 bonds. That means we have 18 electrons left. That is just enough to complete the octets around the outside of the molecule. Because we can give 6 to each oxygen. Right? That's all the electrons we have, though. Don't keep going and add 2 more to the carbon. Right? You kind of have to stop there and then try to fix what's not quite right by sharing. So if we look at the structure, 8 electrons here, 8 electrons here, 8 electrons here on all the oxygens, only 6 on the carbon, so we need to share. Now the question here, and this is the thing that I want you to be watching out for when you're doing this type of analysis, is there more than one option about how to share? So on the handout, right down underneath formal charge, there's another section called resonance structures. This is what we're looking for to identify this particular property of some molecules' resonance. So the definition, again, from that handout, resonance structures are one of 2 or more Lewis structures for a single molecule that cannot be represented accurately by only one Lewis structure. This is one of those. And this is how we know resonance is potential here, is that we find multiple ways to finish the structure. So in this case, we could finish the structure by making a double bond from that oxygen Or we could finish the structure by making a double bond from that oxygen. Or we could finish the structure by making a double bond from that oxygen. But we only do one of those. But each of those leads to a different representation. The first one, the double bond would be there, and single bonds in the other positions would look like this. The second one, the arrow from the top, would have the double bond in a different place. And then the singly bonded oxygens are also in different places. And the third one would have the double bond off to the right, also a different place from where the double bond is in the other two structures. Okay, now each of those, we've satisfied the octet for the carbon, and there's a 0 formal charge on the carbon, but the charge distribution is different in these as well. Negative formal charge on the singly bonded oxygens, so the negative charges are in different places in each structure when we go through and calculate formal charge. Okay. These three structures are what are called resonance structures, or resonance forms sometimes. And that means none of those three structures is exactly what this molecule looks like. This molecule is actually some combination of what is shown in all of these structures. And what I've added in there are what are called resonance arrows. It's a two-headed arrow that is kind of pointing between the different structures. Right? And when we encounter this, right, we encounter this pathway here where we have to pick from multiple options that will all have the same effect as far as finishing the structure. In this particular case, you only show what the molecule actually looks like by drawing all three structures. The molecule is actually sort of a hybrid of all of the drawings. So what is really happening in a carbonate structure is the individual bonds are between the length of a double bond and a single bond. Because if we look at the bond that I have pointed up, it's single in two of the structures, double in one of the structures. It basically means there's 4 bonds spread over 3 structures. The average in the molecule is 1 1/3 bonds. That is something that electrons can do, not something that is easy to draw. And that's why we represent it this way with the resonance structures. There's a similar issue with charge here. We have 2 negative charges looking at the top oxygen in the way I've drawn it. 2 negative charges spread over 3 structures. That means 2/3 of a negative charge is present on each oxygen. An electron can do that because electrons we can think of as waves. They can be in multiple places in our structure in a way that a particle couldn't be. So it is possible to have 2/3 of a negative charge on each of the oxygens in a molecule. That is what the actual structure of carbonate looks like. It's that combination of all 3 of these structures. Now, we'll look at some more examples of resonance, but definitely something to keep your eye out for while you're drawing structures.